Good afternoon, everyone. Well, the topic here is fast, secure, and safe, the web that can still be, because at present I believe that the web that we have is largely not living up to these goals. I am very much interested in Rust myself. I've been working in Rust, but this is not a talk about Rust as such. It will deal with Rust occasionally, and I'll be advocating Rust, but if you want to learn more about Rust, I would expect that David Renshaw's talk, which comes immediately after this in here, will deal more with Rust. At present, web development is in rather a messy state. The way that things tend to operate is that you have a certain amount of time in which to produce something which will go to an audience, and then through that you will make money. The precise way in which you'll make money is questionable. In particular, venture capitalists seem to think that that step is fairly optional at present. And in actual fact, that clock that you have, the limited amount of time, does end up a bomb, because when you've run out of your own money, and if you haven't made enough of other people's money, you shut shop. So the subject matter that we're dealing with today is specifically to do with web servers. I could deal with clients as well, but I think that there's enough to be going on with today. And also there are various things in the way of performance that being stuck with JavaScript you simply can't do. And I'll be dealing with strong statically typed languages, which are not the ones that have tended to be being used in industry. We'll look at some of the benefits that you can get from using a good type system, and also what a bit of performance can do and why it is worthwhile. Okay, who here is not a practicing web developer in any way? Yeah, a smattering of hands. So we don't have a great deal of, and we don't have a great many of them, but let's see. So let's see, we go like that. So we have, let's say possibly 10% that are not using anything. Dynamically typed languages, how many of you use them for your professional web development? Depressing, isn't it? Far too many there. How about languages that are compiled onto and run on a VM? So you've got JVM things there, .NET things. Yeah, I suppose it's reasonable to expect that this is not a typical audience. Here at Strange Loop, you'll have many more people that are familiar with such things. I think in industrial practice, you would have far fewer that would use these in the general way of things. In particular, in small development shops, you don't tend to use those sorts of things. And so, yeah, I will give those ones partial marks. And yeah. And then finally, we have the fully compiled languages. So you've got Haskell, the obscure spider one there, that is a language called which I'll mention it in more detail later. Go, though I'm afraid I don't think terribly much of its type system. C, C++, and Rust, of course. How many people use languages like that? Considerably fewer. I think about as many as weren't doing web development at all. So all these people using the good languages. So this is the problem that we need to see about fixing. Somehow we need to be able to make it so that the poorer quality languages, as I will choose to label them, shrink down and the good ones increase. So I'll be trying to convince you that this is worthwhile doing. So yeah, the solution that most people throw at this problem is your dynamic languages. PHP, Python, Ruby, JavaScript. They use them to produce the things. But the problem is, these languages are rather prone to bugs. There are various things that, due to their weak type systems, or weak type checking rather, they simply don't catch, and so you get various problems that show up later that would simply have been forbidden in other languages. Also, they are fairly inefficient from a performance perspective, and so you end up needing lots and lots of servers. Things tend to get out of hand, and you end up not making the money that you wanted to. Take as an example then a company like Twitter. So they had used Ruby. They want to reduce the number of bugs, reduce the number of servers that they need, make money. How do they do this? Well, the approach that they chose to use was to throw away the Ruby code that they'd used and replace it with Scala. This is a pretty common trend that we've seen in big companies, that they start with dynamic languages, and after a while they realize these dynamic languages really aren't meeting our requirements. And so they end up switching to a language with a better type system. Say Facebook also, they've decided not to replace the language, but to progressively enhance the language in their own direction. And so that's hack. Of course, there's the question, they're still not making money, but never mind. So this whole performance question, I'll compare Ruby and Rust because they start with the same two letters. In Ruby, you have no compile time step. So that is a thing that people very much like, because when you're just starting, it means that you have very, very quick iteration. The development server, once you're getting to serious things, it's pretty common for your development server to take a number of seconds, even up to a minute, to start. And once it is all running, it is slow. A language like Rust, your compilation as a developer, you don't need to worry about turning on optimizations as a developer, for example, so you can get somewhat faster compilation. You're starting with a few seconds for a moderately small thing, but not trivial. The server start time, once you have it compiled, well, it's the sort of thing that I have tended to find with it. When I didn't put in a print message, I was waiting for something to happen, forgetting that it had already started before I'd even finished lifting my fingers from the enter key. And once it's all running, performance is fast. In the Twitter example, the performance improvement that they expected to get was about 10 times. So they had been handling 200 or 300 requests per second per server, and they were expecting to get about 10 times as many. As it happened, they got more like 50 times as many. So now each server, or after the migration, they found that each server was being able to process 2,000 or 3,000, sorry, 1,000, hang on, 10,000, whatever it was, about 50 times as many as it had before. And so they didn't need as many servers. Now here we see a new relic graph. This is from an example of when things aren't going right. So the idea is typically to have this large pale blue section, which is dealing in the dynamic language itself being considerably smaller. But when you're talking about considerably smaller, they're still tending to talk about 50 milliseconds, 100 milliseconds, possibly even more. And it's not at all uncommon to have it being several hundred milliseconds. With a language like Rust, that phase would be indiscernibly small, typically, because the language itself is just so much faster. And so you can fairly easily end up saving a couple of hundred milliseconds per response. complaint that people have about these languages is that compilation time is too much of a burden. Of course, it does give you good excuses for hallway sword fights, but the fact of the matter is that things really aren't all that much better in the dynamic world. Because your test suites, I have heard frequently of people having test suites where the basic version of the test suite takes 7-8 minutes to run. The full test suite takes over 20 minutes to run. These strike me as quite a bit of madness. Or perhaps the package manager is busy updating everything. Because in order to compile our 3 files, we need to download 50,000 files, however many files it was. We are not good at making tools that perform well, really. And it's all just made worse by using dynamic languages. Really, we can come up with any excuse we like. We are very good at making bad tools. So then, this compilation step, what is it doing in that time while it is compiling? I would argue that it is saving you time that you would later have spent finding the problems. You see, in a language like Ruby, you'll go run your code, and then you'll find, oh, I made that mistake. Because once you get to that code path, then it will fail. Then it will go raising an exception or whatever. In a language like Rust, the compiler will have found that for you. Now, people will say that these languages, compiled languages, are slower to work in. And to a large extent, that is true at the start. Initial prototyping, that is faster to do in a language like Ruby. But as the code base gets bigger, it becomes much less maintainable. Let's take a completely synthetic example. I won't bother going through it in great detail there, but there are just various ways in which you end up saving time, though you might not think that you had saved time by using a language like Rust. Various problems that later on you will find and spend time fixing, especially once you've forgotten about how it all worked, where a language like Rust simply won't have that problem. And so you end up having more time to spend in the hallways sword fighting without a legitimate reason. In this synthetic example, you see that Rust is a whole minute faster. So who then is saved time? There is the old adage of developer time being more important than processor time. But especially as a system grows and has more and more users, there are more people that we need to think about. Users. If the response time is decreased, the users are made more happy. In particular, in the realm of e-commerce, there are very clear known connections between the response time and the revenue. If you shave time off your response time, then your revenue will increase. There are also very interesting ethical concerns to doing something in a dynamic language. Say the ACM, for example, their code of ethics. If you sincerely believe that a language like Rust is superior and is going to produce a better result for the end user, it actually ends up unethical using a language like Python or Ruby. It's an interesting aspect that people don't think so much about. And yes, in the talk about type systems, the good, the bad, and the ugly, the whole question of SLAs was raised. If you have an SLA, not using a good type system is unethical, they claimed, which is an interesting perspective. Developers, as I said up front, you are probably not going to be saving time by using a language like Rust, but in the long run, I believe you will be saving time. On a mature system, you can just be sure that you can make much more wide-ranging refactorings with confidence because the type system is there to help you. And also, because you end up with fewer bugs, or I will claim so at least, you will end up with fewer users being annoyed and fewer distractions from getting more work done. Servers, you end up with considerably lower resource usage. Say, I would compare, for example, NewsBlur. At one point, I had gone estimating how many servers I reckon that they would be using. It's a Django thing. For the number of users that it had at that time, I estimated that it would probably have something like half a dozen servers. A few days later, completely by coincidence, he published the numbers, and actually it was 52 servers that were being used. Those are fairly small servers, so it's not such a terrible thing, but it was the sort of thing where from the actual workload being performed, there was no reason why it should take more than one server. In a language like Rust, I would tend to say it would have taken one server, except you'd probably go for having a second server for redundancy. A place like Stack Overflow, they have less than a dozen servers running all of their sites using .NET, so using something which is distinctly faster than your dynamic languages, though not optimal. And they could reduce it to fewer servers still, they say, if they really wanted to. So you can end up saving money in those areas by using a faster language. And also there is the question of security, which is what I will then continue to be speaking about later on here. The type system of a language like Rust can help you to simply structurally avoid various classes of vulnerabilities which have been causing lots and lots of trouble. And a security vulnerability is a very expensive thing. There is the matter of patching it up at very short notice, notifications to people, loss of confidence. It's something that you want to avoid if you possibly can. So now, why you need a good type system? HTTP headers. There is a very common notion, which is absolutely wrong, that headers are strings. They are not strings. They're stringly typed in almost every library you'll find out there. There are a few which aren't, mostly in the Lisp and Haskell worlds. But in most languages, headers are strings. This is semantically wrong. Now, here we see some Rust code. See, we did finally get to some Rust. Up the top there, you see what a language like Python would be doing with this. So the do not track header, it has two possible values, 0 and 1. 0 means you are opting into tracking. 1 means you are opting out of tracking, and the absence of a value means that you don't care or haven't expressed a preference. So normally in those languages, your headers thing will just be a dictionary, hash map, whatever you wish to call it, of header names and values as strings. And a simple example like that, it works okay. But in a language like Rust, we can end up with something like this, where just by virtue of that value that we have there, DNT, that is linked up using the type system so that the return type of that function will be appropriate. In this case, it's an enumeration which has opt-in and opt-out. That is a very trivial example. It scales up considerably further though. Say, for example, if you have a header that accepts a date, in most places you'll just get a string which is representing the date in the appropriate format. And people will do all sorts of horrible things with that string, trying to get it into a format that they understand. And they will depressingly regularly make a mess of it. So let's look at just how this is then implemented here in Rust. So first of all, we have the enumeration, which is the return type of that method. And then we need to specify for it both how the header is parsed. Now, note that the raw representation there, that is 2 levels of lists. Because another thing that people regularly forget about headers is that it is not necessarily just a single value per header. So, for example, you can have 2 DNT lines. So in this case, then, we just say that if we have a single header field for that, and it has the value 0, then we say, yep, opt-in, 1, no, opt-out. And if it's anything else, then we say this is an invalid value. and we return none. Likewise, when it comes to formatting of the header, this is the sort of thing that could be done more neatly, but it's done using a writer so that it is more efficient at execution time, so that you don't need to go creating a new string or anything like that. And yes, we then just convert it straight back to that. And then we have this header marker at the bottom. That's just a simple macro. It expands to something like that. It's actually not precisely that. It's using their associated types, which is something that is in the process of landing in Rust. The way that this is implemented in TP, my HTTP library at present, is actually using generics. And so this is the part that links up the value that we passed in, which is, so DNT, that is a 0 size type. And it then says, well, when we're doing that, the type that we will parse that header as, which incidentally is the string DNT, so that's the name of the header as it is on the wire, it will be interpreted as that type. This then is the implementation of the actual header traits and the header collection. I won't go explaining the details behind the Rust parts of it terribly much. But yes, the trait is basically just an interface, if you're familiar with them from other places. And yes, the header marker, as we need it there. The important stuff is here. The header collection, it is actually stored as a mapping from strings to items, where the items are either a raw value or a typed value, or if it can demonstrate that it won't go wrong, that one of them won't be changed, it can actually have both. And then you have, on your header collection, you have your methods like get. You can also access the raw representation and set it. And so then you pass in your header marker, and it will return an optional thing of that header marker's header thing. So in the case of the DNT all in capitals thing, that is the DNT with lowercase nt type. In the case of say the expires header, you would have your structure expires, and its associated header type would be the time type. The really good part about all of this is that it can't possibly go wrong. The type system has ensured that all access to the headers is strongly typed, and also that the types will be correct. Additionally, there is the fact that none of these header types are privileged. So standardized HTTP headers, they do not get a special position. If you have two different libraries that both want to interpret a header with this name, they can do that, and it won't go breaking. It will allow them both to access that thing as their own type, and that will work. So the type system is allowing you to do something which is much more useful, but which would be distinctly hazardous in a dynamic language because of the lack of the type checking. And it lets you do it and know that it's correct. Just want to emphasize one more time, headers are not strings. That's merely the wire format. This language, then, it is actually something that is production ready and highlights a lot of these things. It's something that deals with full stack web apps, so server and client. It's the entire thing. I believe that it actually compiles down to C, but that's comparatively irrelevant. It's a language in ML and Haskell traditions. But let's look at some of the things that it allows. Compare it in your mind with a language like Ruby and what Ruby on Rails gets you. So you still get to use your SQL databases, but they simply don't go wrong in various ways. So code injection attacks, they simply can't occur. The type system has ensured that they cannot occur. Invalid HTML. All your HTML is compiled into the program, and it is parsed at that time. So it simply cannot emit structurally invalid HTML. Links inside your application, it is able to guarantee that you won't have any broken links because all of them are semantically known. You won't get the common problem where the front end and back end are developed separately, where the client sends the wrong things to the server. Things like that. Invalid SQL, Bobby tables, he has no place here. All of these things are things that in your dynamic languages, they are constantly trying to patch things to fix up problems, make sure that it works pretty well, but it's never perfect. Whereas in a language like this, it can be. Let's take as an example this thing. This is the sort of thing that Django, Rails, they will make a mess of because they have only a single notion of escaping. They escape into HTML. Down here, you're wanting to put it into JavaScript. Escaping things in JavaScript operates differently. You don't have the same things that you need to escape. So say your less than and greater than symbols, if you go escaping them, all of a sudden your mathematical operations are rather limited in functionality. And say in the case of C there, if you have a string with a closing parenthesis, all of a sudden you've messed up your CSS. There's the possibility for injection there. A and B, those are the only things that they really deal with properly because it's designed for HTML escaping. So tainting systems, these escape mechanisms, they're simply not good enough for meaningful security and also correctness, because correctness is a very important thing here. In a language like Rust, you can have it that all of these things can be appropriately type checked. So, for example, in the third case, C, there you know that a URL must be there. So at compile time, it can go parsing the entire thing, including the CSS and JavaScript, and form an appropriate syntax tree of it all. And it can realize that C needs to be a URL. If it's not a URL, that would be wrong. And these are the sorts of things that you can achieve with a type system like this. Templates in Django, I have observed to be the thing that people most frequently make a mess of, because you end up with files all over the place and very frequently they're broken. Also, Django's default of just silently ignoring missing variables and things like that, that leads to many more problems. You get the same basic approach in SQL. This is something that you can actually go and see in use. Say, for example, there's a Rust Postgres library, which uses precisely this pattern of being able to convert values to SQL types, and thus structurally ensure that you can't have injection bugs. They simply cannot exist. They are illegal and cannot be represented in the type system. There's an article that I have linked there, that the article just entitled Structurally Fixing Injection Bugs. It goes into these topics in quite a bit more detail, and it does a very good job of highlighting why a good type system is important. There is a lot more in Rust that is worthwhile talking about, but which I won't go talking about. Its ownership model in particular is something that I have been very sorely missing in Python, because I am employed as a Python developer still, though if anyone happens to want to hire me for working in statically typed languages, especially Rust, I'd be delighted. But yeah, Rust's integration with dynamic languages, Yehuda Katz and Tilde, their project Skylight, an error reporting thing like New Relic for Ruby, its agent is written almost entirely in Rust and has been for many months, because they simply decided that Rust was the only appropriate language that they could find for it. Because of Rust's lack of garbage collection and so on, it can fit in very well with these other languages. So then the summary. If you wish to reduce bugs, reduce the number of servers you need, make money, make your customers happy, try throwing away your dynamic languages and use a language like Rust, or experiment with a good type system. Of course, you will need to go with both the existing things and the new things, but it's all worthwhile experimenting with, just to see what's possible, because you might discover new things that you hadn't realized before. Questions? How much time do we have? A few minutes. Yeah.
On the topic of SQL injection bugs, right? If you're going to be, so the classic SQL injection bug is PHP, right? So someone has some get parameter that comes in and then it gets interpolated into a string of SQL, and then get passed to the database. And they do it that way because they're too lazy to use binding parameters, right? But so every modern SQL library has these bind parameters, and once you use those, you more or less don't have SQL injection unless you're constructing your SQL bit by bit out of strings. But you can construct your SQL bit by bit out of strings in Rust too. What's to prevent you from accidentally interpolating a user string in there?
So the question was, well, really to do with interpolation and how can you avoid the problems, because in all your ORMs in dynamic languages, they have appropriate safe interpolation techniques. In a language like Rust, you simply get to the situation where these problems cannot arise because the type system simply cannot represent them. If you wish to go exposing an untyped query thing, which allows you to just execute an arbitrary SQL statement, you could easily choose to mark that as an unsafe function, so that a user has to be explicit that they are calling an unsafe function. Or you can simply omit that and require people to use the strongly typed access. Say, for example, in TP's header representation, at first I was not convinced that I should even allow raw access. But I ended up being convinced that, yeah, allowing people to access the raw headers is actually important. But also in a language like PHP, why do these problems still exist? You still observe newbies coming to the language and making mistakes because the language doesn't enforce these things in any way. That's the problem. Rust allows you to be confident that it's right. Yeah?
So that's actually an interesting point. So one of the things about security is that all your strong links don't make any difference if you've got a weak one. So are you really, how confident are you?
The question is, how confident am I of Rust? Because all it takes is a single weak link to take down an entire otherwise strong system. I came to Rust because I believe that these things are possible and that it is possible to make a completely safe system. I don't believe that Rust is the be-all and end-all of things. There are various things like dependent types, which I rather yearn for now that I've seen them. But Rust, I think, is likely to succeed at present. It has the impetus, the social impetus. It is growing well, and it has enough of a good type system that we can, at the very least, use it as a good stepping stone towards something even better still.
Is it still hacker-proof, would you say, or foolproof?
More than anything else, I would tend to say. So it's still not going to be perfect because there are still humans involved in the system. If we could just get rid of humans from the system, it would make the security problems so much simpler. But I would tend to say that at the very least, it is enormously better than the state of the art at present. Yep.
Hey, if you had a recommended person moving from, I guess, Ruby or some PHP, would you recommend that the first language they move to as Rust, or are there any other easier languages for somebody to dive into?
I start, so the question being, do I recommend going straight to Rust from a dynamic language or via other things? I went from Python being my main language, not having really dealt with statically compiled languages before, and I didn't find it excessively difficult. Within a few months, I was absolutely fluent in Rust. As for the immediacy of it, well, Rust is not production ready yet. It is a longer goal. If you want something that you can use now, you might like to say experiment with /web, or Scala also has quite a lot of good stuff. What's the time? Yeah, out of time really.